Welcome back. I've got a joke to get us started. What is a statistician's favorite? Wait, what was it? Hold on, bear with me. What is a statistician's favorite kind of joke? A normal one, but only if the mean is funny and if the variance isn't too large. Uh, can these intros get any worse? I think I've just proved yes. So, sorry, I'll get straight to the statistics. So I know you're hungry for more statistics, so let's get straight into it. The intros will be much sharper after this. I have no more jokes. So, which extraction method do you use? There are two main approaches to extracting factors: principal axis factoring analyzes shared variance, and principal component analysis, which analyzes all variance. Sorry, I'm stumbling on my words because I'm just on edge about the bad joke. So the key takeaway is so we have all the variance that's there. If you're analyzing the shared variance of factors, you're using principal axis factoring. If you're analyzing all the variance using principal components analysis, don't worry if that doesn't make sense. I'm going to go into it in detail now. So principal axis factoring, when is it used? It's when you're trying to discover the underlying structure of a set of variables. So it's really theory driven, and it analyzes only the common or shared variance. So it leaves out variance that is unique to each measurement item. So it's only what variance is shared between the items. And it's really when you're trying to discover the underlying structure of a set of variables. But principal components analysis, it's more common, but it's used to reduce many variables down to a smaller number of factor scores, which can then be used in other analyses. So it analyzes all the variance in each variable, common and unique, and then it tries to synthesize that down into a smaller number of factor scores, and then you create the composite score there, and then use that forward. So so again, principal axis factoring, discover the underlying structure of a set, and then principal components is like this synthesizing data down into its fundamental smaller number of factors. I'm not sure if does that help. Hopefully that helped you, like synthesizing data down. Yes. And the variance. So the variance of a variable is made up of, you have common variance and unique variance, right? So these aren't really statistical terms. It's just a sense of understanding when it comes to these variables, what overlaps and what doesn't. That's all it is. So we hopefully have a good sense of what variance is now. Remember, when we're thinking about the spread of data points around say a mean or average or the line of best fit, you have the spread of data points that are there, and then which is the total error that we sum up, or squared errors, and then we get the variance. Now the shared variance of how these variables come together, the shared variance that's there, that they account for in one another, and that's common variance. And that's what we see in this sort of overlapping structures here. So this is common variance between this one and this one, common variance between this one and this one is here, and here this little spot here is the common variance between all three. Now unique variance are these sort of sections here, which isn't shared by the others, right? So that's common variance is shared with the other variables, unique variance is not shared with the others. So the question is, which should you use, right, when we're talking about principal components and principal axis? So why was that important? Because principal axis factoring only analyzes that shared variance, this shared variance that's here. But principal components analyzes the unique variance and the common variance. So when do you know which one to use? Well, practically, actually, there's often little difference between principal components and principal axis factoring. If they come to different solutions, try and work out why and decide which is more appropriate for your data. It's an iterative process. It doesn't have to be something where you're committing to it has to be principal axis or principal component. You can typically have a look and see which one fits the data best. But typically, the purpose or the theoretical purpose can drive it a lot. So often people, if they're interested in like data reduction, they'll use a principal components analysis to get that data down. And the goal is really to explain the variance. So a good factor solution is one that explains the lion's share of variance with the fewest factors. And A good regression model is one that sort of accounts for the variance in the data, right? I've seen many papers that look at relationship between variables or whatnot, and then they report a statistically significant effect, and they say this is the effect that we see, and this is the effect size if you're lucky to see that in a paper. And then you look closely and you say to, I've had this in a case where I was reviewing a paper, and you see that actually they say that these are the results, but when you look at the amount of variance that's explained, it's like 0.01%. So if you look at all the data, the line fits 0.01% of the data set. And it was something extreme like that in the example. I think it was less than 1% of the data that was explained. I'm not sure exactly the number. So the question then becomes, what do these results mean when over 99% of the data is not accounted for by, or the variance is not accounted for by the model you fit to the data? And so a good factor structure, our sense of understanding of the world around us and understanding of the data comes from the amount of variance that we can account for. And so if we can explain or account for 50 to 75% of the variance, that can be great. But it's, again, don't be too strict on the rule. It's just a guideline that's there. So here is our example, again, coming back to that example of the brain health and using the different measures of getting a sense of brain health for cognitive worry or what you're doing as in your behaviors to sort of address that. So this is an example of principal access factoring that's there. And what I want you to focus on, these SS loadings relate to eigenvalues, and we'll come back to that in a moment. But we can see that there's 3 factors that are here. And so the proportion of variance accounted for by this, explained by this model, is 28% in factor 1, 11% in factor 2, and 9% in factor 3. Right, and then the cumulative variance is just adding this, so you get a sense of the total variance. So this is 28 because this is 28, and this is 39 because you've added 11 to 28 to get 39. This is 48 because you added 9 to 39 to get 48. So this allows you, the cumulative variance row allows you to say, oh, 48% of the variance is accounted for. So in some ways I intentionally did that to show you that it's less than this rule of thumb, so don't be too strict on it. I wouldn't be throwing away this just because it's 48% of the variance. It certainly is a large amount of variance that's accounted for. The proportion explained and cumulative proportion, don't stress too much about that. What, if you're interested, what it means is of this 48% of the variance, how much is accounted for by variable 1, right? And so of this 48, it's just 28 over 48 gives you 58%. And then 11 over 48 is this, and 9 over 48 is 19. So that's what that is. And then this is the cumulative explained proportion. So 58, 23 plus 58 is 81, 19 plus 81 is 1. The main takeaway from this table, which is which produces the eigenvalues, is just seeing what is the total variance. So this number here, 0.48, the cumulative variance accounted for by all these factors is 48%. So communalities, what are communalities? The communality of a variable is the proportion of a variable's variance explained by the extracted factors, right? So you've done your analyses, you have your factors that are there. Communalities allow you to understand, well, how much of the variance in the variable is accounted for by these factors? So communalities range from 0, so the factors don't explain any of the variance in the variable, so no variance explained, to 1, all the variance explained. So to interpret this, if it is greater than 0.5, this indicates a high communality. So the extracted factors explain most of the variance in the variable. If it's lower than 0.5, this indicates low communality. So considerable variance in the variable is unexplained by the extracted factors. Again, communality is you have your factors that are there, and how much of the variance in the variable is accounted for by the factors. So what do you do when you have low communality? Well, if the variance in the variable isn't really well accounted for by the factors, you can either eliminate the item, take away the variable, or perhaps you needed to extract more factors, and then that variance would be accounted for then. So either extract more factors or eliminate the item. So here's an example of communality. So here is our simulated data, which has our 12 items and of the cardiometabolic measures, cognitive measures, and self-efficacy measures. And we can see of the factors that we've extracted, of the 3 factors we've extracted, the variance in cardiometabolic, that question 1 was 52% accounted for, 60%, right? And so you can see throughout this, you can see all the variance it's accounted for each of these items. What's interesting to me is this self-efficacy 4 item, which has about 0.3 that's accounted for, right, in the communality. So if it's greater than 0.5, it indicates high communality. If it's lower than 0.5, it's low communality. So what's I'm saying here, of course, yes, there's some that are 0.48 and some that are 0.45. It's sort of borderline, but they're all sitting around roughly the 5 mark. This 0.3 really sticks out to me. And so I would be asking myself the question of, is that item something that is properly accounted for by the factor that we name here? Or is it that I should remove it? Is it that perhaps there's maybe an extra factor that would account for one that would count for self-efficacy 1, 2, and another that would count for 3, 4, and then the variance accounted for would increase as a function of that? So these are the questions to be asking with the communality table. Eigenvalue, I mentioned it very briefly. Let me explain what it means now. So each variable contributes to the variance that needs to be explained. So each factor tries to explain as much of the total variance as possible. You have 100% of the variance trying to be explained, and every factor tries to explain as much of that variance as possible. An eigenvalue indicates the amount of overall variance that each factor accounts for. So essentially, here is an example of eigenvalues. We have 3, 1.3, and 1.1 for our 3 factors here. So an eigenvalue, typically when eigenvalues are over 1, they're considered stable. This is called Kaiser's criterion, and that's the typical rule of thumb. So eigenvalues for successfully extracted factors successively extracted factors have lower values. So when you look at and we'll look at one in a moment, if you have in this example, we have 12 items. When you do your analysis, you'll have 12 factors. And here are examples. So here's 12 factors that we have in this model. And so every time you do a factor analysis, however many items you have in your survey or questionnaire or whatever construct you're looking at, that's the number of factors that you will get. Your job as the researcher is to say, well, what is the factor structure? How many factors should we be looking at here? And so that's really the purpose of what we're doing now, because when all of these factors total the cumulative 100% of variance that we're accounting for. So eigenvalues can be used to express as percentages of explained variance. So the total of all the eigenvalues is equal to the number of variables, or 100%. So if we were to add up all of these eigenvalues, we should get 12, right? So total of these eigenvalues adds up to the total of variables that you have, and you can use it as a proportion. So again, our job here is to look, well, how many factors do we have? Now, of course, the Kaiser's criterion says if it's greater than 1, it'll be stable in the factor structure, but maybe there's more than 3 factors. Maybe there's 4, 5, 6. I don't really know just looking at this table. The question to look at, or the diagnostic tool to look at, is what's called a scree plot. So this is a scree plot. Hopefully it looks interesting to you. Now let's dissect what it means. So this is our analysis of our data. So we have the 12 factors that are there, and it just plots those factors that are there against the eigenvalues. And so what we're looking for here is, where is the elbow of this scree plot, right? And when you look at where the elbow is, I would say there's sort of 2 elbows or inflection points. There's one here between at 2, and there's another inflection point at 4. And so what we want to do when you see the inflection point is you want to go one left to it. So you looking at this scree plot, you would say either there's 1 factor structure or there's a 3 factor structure. Again, how did I come to that? Because I can see the scree, the elbow point is at the 2 and elbow point's at the 4, right? And then it flattens off. It becomes the scree that we see. And so what you want to do is identify that point of the elbow. Where does it flatten off? And then go 1 back. So here the point of the elbow is 4. So I'd say there's either a 1 or a 3 factor structure that's here. How do I determine which is which? Well, that's where we need to see what those items map onto for that factors, and build from there. Now, I don't really see any other major inflection points, so I wouldn't say that there's any further ones. But in this example, it just so happens that all of the factors are above 1. It may be that you have another inflection point after this, below this 0.1. Maybe you have an inflection point here, and you say, actually, maybe there could be 4 factors, but it's not. It's less than 1 for the eigenvalue. That's okay. You can include it. That's where you go to the items and see, well, is it meaningful? You can look at the communalities and get a sense of whether the variance is accounted for appropriately there. And notice that there are 12 factors because there's 12 items. So have a go at this one. Based on the scree plot, how many factors would you retain? Do you think it's a 2-factor structure, a 3-factor structure, or a 4-factor structure? I don't know why I'm waiting. I fell into the trap again. Pause the video and then restart it when you're ready. And so what you're looking at here, hopefully it becomes clear that it's actually a 3-factor structure. Why? So there's a clear elbow after the 3rd factor. So you see this elbow here. The first 3 factors certainly explain most of the common variance, and factors after that explain relatively little, right? But really, you see the elbow point, the inflection point that's here, and you go 1 left. So the inflection point happens at 4, and so you go 1 left to that, so it's a 3-factor structure, and it happens that they're all above the 1. So a scree plot is a line graph of all the eigenvalues, and that's what we see there. So this eigenvalue, all of these eigenvalues here, they're just plotted here for the scree plot, right? And so that is what allows you to determine, it shows how much variance is explained by each factor from the most to the least. And you use it to decide what the best number of factors is. Look for the elbow, the point where additional factors do not account for much additional variance. So yes, for example, here, maybe you could say there's a very slight inflection point at 11. And so would you argue for 10 factors? Well, the gains you get from a 3-factor structure to a 10-factor structure are so minimal because the amount of variance accounted for by these factors is very small. So you've got to always weigh it up. This is why typically you wouldn't be taking too many below the 1 threshold. It may be 1 more or perhaps 2, but really not much more, because if it's less than 1, it's not really accounting for a lot of the variance in your overall model. Excellent. So that is that. So it shows variance from, and look at the elbow point with additional factors do not account for much variance. So here's another practice question. Building on your knowledge of eigenvalues and variance, so an exploratory factor analysis has 20 variables. Indicates that there's 4 factors explain 60% of the variance. What do eigenvalues of factors 5 to 20 add up to? Take a pause. Try not to let it get too overwhelming. Try to think about what we've learned so far and get a sense of how you would work this out. So if you've come back, hopefully you didn't say impossible to tell. It is possible to tell, and I'm going to show you how. Essentially, you have the way to work this out is understanding that if you have 20 variables, they make up 100% of the variance. If you remember from here, the number of variables equals 100%, right? And the total of all eigenvalues equals the total of number of variables. So in this example, I have 20 variables, which means I'll have 20 eigenvalues, right? So the eigenvalues will sum up to 20, and I'll have 20 factors, a 20-factor structure. So the first 4 factors explain 60% of the variance, right? So what do eigenvalues of factors 5 to 20 add up to? So I know that 5 to 20 make up 40% of the remaining variance, right? So 40% of the remaining variance is made up there. And so the way to work it out is you can go 40% of 20, which should give you 4 over 10. Yeah, so 40% of 20. Yeah, so you get 4 over 10 of 20, which is 8. So to work that out with you again, you have 20 variables, which means you have 20 factors that are there in your factor structure, which all make 100%, right? So 20 variables, 20 factors, they make up 100%. The eigenvalues will add up to should add up to 20 when in this example, and we find out that the first 4 factors make up 60% of the variance, right? 4 factors make up 60%. So how many factors are left? Well, there would have to be 16 factors left, right? So, and that's here, right? This is not the exact example, but imagine there should be 16 factors if this went to 20, because each of them represent the variables. So what do the remaining 5 to 20 factors add up to? Well, eigenvalues add up to? Well, we know that if the 4 factors is 60%, then the remaining should add up to 40%. And so what are the eigenvalues add up to? Well, the first 4 factors add up to the first 12 eigenvalues. So the remaining 60% is actually the remaining 8 eigenvalues that are there. So understanding those relationships will help a lot with working out. So you can convert variance to the variance explained to working out how many eigenvalues because of this relationship, because of the fact that if there's 12 factors here, if there's 12 questions, you'll have 12 factors, and the total of these eigenvalues will total to 12. Sorry if I'm over-explaining this or explaining it too much, but I think it's important to know that relationship so that when you look at an eigenvalue, it connects a bit more and you say, oh, okay, so if it's 3.83, I can work out the percentage of that. It's 3.83 over 12, and that's the percentage of variance that's going to be explained times 100. So that's where you get a sense of why is it that 1 is the threshold. Well, typically if you have 12, 10 or 12 or even higher number of factors, it's not really accounting for a lot of the variance that's there. Yeah, excellent. So that's free plot. We've done that question. So how many factors do you have is the big question. So Jamovi will give you the same number of factors as variables that you have. So that's what we were emphasizing before. So if you have 12 variables in your survey, you'll have 12 factors. Now there's no definitive statistic that tells you how many factors to choose, which is why there's such a focus on justification when it comes to statistics. You say, here's the theory, here's what the statistics show, and here's my justification for why I think it is the way I think. And so how do you make your decision? So which solution explains the largest amount of variance with the smallest number of factors? So of course, if you have more factors, you'll have more variance explained. The question is not, okay, well, then I should choose a 12-factor structure. It's no, actually, do you make any additional gains by choosing a 3-factor structure versus a 7 to 8-factor structure? So that's the first thing, right? What explains the most using the minimal number of factors? And what did the theory say? What did you predict in terms of the factor structure? What do you expect? Which eigenvalues are greater than 1? So of the total variance explained. Where is the elbow plot in the scree plot? Can you make a convincing argument that you can see those inflection points? How interpretable is your last factor? And which solution fits best? So, for example, what's the type of exploratory factor analysis, the rotation, and the number of factors? So keep these things in mind, and we'll talk about rotation in a moment. So I think with all of these, they all have important weight and merit, but certainly you want to be asking yourself the interpretability of your factors. Can you truly interpret something from your factors, the items that load onto that factor? Can you make some, so I've emphasized this here, so your factors must be interpretable and they must make theoretical sense. If you're making an argument like, oh, if I have a let's take this example, I have a 4-factor structure or 5-factor structure, and I've chosen it because it explains X% of the variance. That alone won't be sufficient justification if factor 4 and 5 make no theoretical sense, right? So this is really where the researcher comes into play in statistics, and you make the decision of, here are the items that load onto the factor. I think the factor represents this. That's why I think that it's an X number of factor structure, and I have these statistical tests to support this thinking. So that's really, these are all the things I want you to be thinking about with the factor structure that you're developing when you're researching. So also keep in mind, remember that an exploratory factor analysis will keep going until it has extracted the same number of factors as you have variables. You should be aiming for a solution that explains 50 to 75% of the variance, explained by a quarter to a third as many factors as variables. These are just guiding principles or rules of thumb to give you a sense of like how many you should be choosing. Ultimately, it can be useful, and essentially you want to stop extracting factors when they no longer represent useful or meaningful clusters of variables. So when you get to the point of saying, oh, I could add one more and it improves this or improves that, but if the item, it doesn't make sense as to what the items are loading onto, and you're not able to have an interpretable factor, then that's a good signal to say, well, maybe I needed less factors, and maybe I need to consider removing items. Maybe they don't actually load onto the factors that I was hoping would be there, or I was expecting to be there. So that is the process of determining your factor structure. So the more you do it, the more practice you get, the better and more confident you'll be at determining that. So again, here's our simple conceptual model. These items load onto two underlying factors. The items represent, tap, measure what that construction or construct or factor is. The factors are made up of relatively similar related variables or items. That's what we see there, right? So these are the factors and these are the items. I just want to have it sort of the visual representation of what's going on behind the statistics, because you've heard of all these words: communality, shared variance, unique variance. I just want you to identify at the end of the day, we have these items on a survey and we're trying to see, well, do they cluster? Do they share this relationship with one another, the correlations between them, which allow you to say that they represent something meaningful, a meaningful construct, not a construction, sorry, but a construct there. And so that's the key. So a factor loading matrix. So before, what we'll do now is we'll take a break, go have a tea, come back, and we'll get back to the factor loading matrix. So I'll see you guys very shortly.